Have you ever just stopped and wondered about the simple stuff? I mean, really thought about it. Like, why is it that a metal cable charges your phone without a problem, but a rubber band is, well, completely useless for the job? The answer is hiding deep down inside the atom, and believe me, it's an incredible story. So, let's follow the electron and see where its journey takes us.
Yep, that's what we're going to do. We're going to follow the journey of this tiny, negatively charged particle all the way from its home inside a single atom to its role in powering our entire digital world. It's this journey that explains, well, pretty much everything. Okay, so to understand why copper conducts electricity and rubber doesn't, we have to start small. We have to understand the playground where our electron lives, the atom. The properties of every single material you've ever touched are decided right here, at this unbelievably tiny scale.
Now, our picture of the atom didn't just pop into existence. It was this amazing scientific relay race. First, you had Dalton saying atoms were just tiny, solid balls. Simple enough. Then, J.J. Thomson discovers the electron and figures it must be mixed into the atom, kind of like plums in a pudding. Then Rutherford comes along and finds a tiny, dense, positive nucleus, giving us that classic solar system model. But there was a huge problem. The physics of the time predicted the electron should just spiral right into the nucleus, and the whole universe should collapse. Whoops.
And that's where Niels Bohr just changes the game completely. He came up with this radical idea. He said, what if electrons can't be just anywhere? What if they're restricted to specific, fixed energy levels, like cars in designated lanes on a highway? As long as an electron stays in its lane, it doesn't lose energy, and the atom stays stable. So the big takeaway is this. Electrons have very strict rules about where they're allowed to be. This idea of fixed energy levels, it is the absolute key to everything that comes next.
Okay, so we've got a handle on a single atom, but the real world is made of billions and billions of them all packed together. So how do they, hold hands to form solids? It all comes down to how their outer electrons link up through chemical bonds.
And there are a few ways they can do this. You've got the ionic bond, which is basically a transfer. One atom just gives an electron away to another. Think table salt. Then you have the covalent bond, which is more of a partnership. The atoms share their electrons. That's what holds a water molecule together.
But for our phone charger question, the one we really care about is the metallic bond. And this is so cool. In a metal, the atoms basically throw all their outer electrons into a giant community pool. They create this sea of electrons. These electrons don't belong to any single atom anymore. They're totally free to just flow anywhere they want within the metal. Remember that idea. That freedom, that sea of electrons, is exactly why metals are such amazing conductors. Now, in other solids, like the silicon that's in pretty much every computer chip, it's not a sea. It's more like a perfectly built city. The atoms lock into this incredibly precise repeating pattern called a crystal lattice. You can see how each silicon atom is perfectly connected to 4 of its neighbors. It's this perfect collective structure, this atomic cityscape, that completely changes the rules of the road for our electrons. And this is where it gets really, really cool. When you bring all those billions of atoms together into that perfect crystal, Bohr's neat little energy levels are forced to interact. They get squished together, and the rules of the road change completely. They create something new, energy band superhighways.
Just look at this diagram. Over on the right, you have your individual atoms, with their nice, sharp, separate energy levels. But watch what happens as you push them closer and closer together to make a solid. See how those levels start to merge and smear out? They spread into these wide, continuous bands of allowed energy. Those single lanes become massive multi-lane superhighways.
So we give these 2 most important highways special names. The valence band, think of this as the home band. It's where the electrons normally hang out, holding the atoms together. Then, above that, you have the conduction band. This is the express lane, the superhighway. If an electron can get enough of an energy boost to jump up into the conduction band, it is totally free to move and create any electric current.
And this brings us to the big payoff. The entire electrical identity of any material in the universe, whether it conducts, whether it insulates, or something in between, it's all determined by the space between these 2 bands. It is all about the gap. And this diagram just shows the 2 extremes perfectly. Look at the one on the left. That's an insulator. That's our rubber band. See that gigantic energy gap between the 2 bands? An electron would need a massive jolt of energy to make that leap, so they just stay put, no current. Now, look all the way to the right. That's a conductor, our metal cable. The bands actually overlap. There's no gap at all. The electrons can just cruise onto that superhighway with practically 0 effort.
But right in between these 2 extremes
is where the magic happens. Here we have the semiconductor. This is the Goldilocks material. It has an energy gap, but it's small, it's manageable, it's not a natural conductor, but you don't need a crazy amount of energy to get electrons to make that jump. This small, controllable gap is the secret to its incredible power.
You can see this so clearly on a chart of electrical resistivity, which is just a fancy way of saying how much a material fights against an electric current. I mean, look at this scale. On one end, you have conductors like copper with almost zero resistance. On the other end, insulators like glass with resistance that is just astronomically high. And right there, sitting perfectly in the middle, you've got the semiconductors like silicon.
So, because that gap is small and controllable, it means we can actually hack the semiconductor. We can fine-tune its conductivity by intentionally adding tiny amounts of impurities. This process is called doping, and frankly, it's the foundation of our entire modern world. So here's how we go it. It's really clever. If we take our pure silicon and we sprinkle in a little bit of arsenic, which has an extra electron, well, that extra electron is a free agent. It has nowhere to go, so it easily jumps into the conduction band. This gives us what's called an N-type or negative-type semiconductor. Or we can add boron, which is missing an electron. This creates a little empty spot, a hole, in the home band, and that hole can move around as if it were a positive charge, creating a P-type semiconductor.
So what happens when you cleverly place these N-type and P-type regions right next to each other? You create something called a PN junction. And that junction, that's it. That's the fundamental building block of almost everything electronic. It's the heart of diodes that control current and transistors that act like microscopic little switches and amplifiers. We put millions, even billions of them on a single chip.
So there you have it. We went from the mystery of a single atom to these vast energy band superhighways that define every material, and then all the way to the art of hacking those materials to build a modern world from basically sand. This incredible atomic-level control is what gave us the entire digital revolution. And it really makes you wonder, doesn't it? As we get even better at this, what will the next great material breakthrough unlock for us?